All right, everyone, welcome back. I think today is Monday. I'm not totally sure for all the reasons that I've said a multitude of times. We are starting our third lecture on rotational quantum mechanics. We've got we did two lectures of 2D, now we're going to do two lectures of three-dimensional rotation, and then we're going to get into the hydrogen atom. Now, unfortunately, I have to warn you, this is the hardest part of the class. That begins today. We'll have about a week and a half of this. And then we're going to be done, we're mostly done with quantum. So we're actually looking at the end of the tunnel here coming up. The end is sooner than later, right? And the way this class builds upon itself, of course this is going to be the hardest part. But we're going to finish up this whole quantum mechanics, this and that. We're going to get to atomic structure, which has quantum elements in it. As usual, we're going to set up the Schrodinger equation and look at wave functions. But once we're looking at like hydrogen wave functions, that'll get easier. And then we're done. We're then going to look at spectroscopy, which I guarantee you is going to be easier. Then we're going to do kinetics, which is, by the way, the easiest subject in the course. I saved that for last because you're seniors and I know that you have other exams. And I know you're getting kind of tired of all this. So I'm saving the last week and a half for kinetics, and again, that is going to be child's play compared to what you've done. So heads up on that. I forgot my watch, so I'm going to have to check with Siri every now and then, which you know that thing has a way of back talking. So sorry if I appear a little distracted every now and then. All right, well, let's see. I did not quite finish up the discussion of the 2D rigid rotor, which is fine because I want to review a little bit as well. So I'm going to talk about one or two of those things I didn't discuss, I didn't get to on the last lecture, and that will be a way to remind you what this is. And the thing that's important about this, to realize why I just probably scared you and traumatized you talking about that we're going to get to some harder stuff, it's because the 2D rigid rotor, here, just a reminder, the 2D rigid rotor, remember, that's in cylindrical coordinates, and I got a new pen. It'll hopefully wake up. It just takes a few minutes, and it'll the ink will flow or something. This is in a plane, right? It's in a plane. The z direction does not exist. It can't pivot into the z direction as it rotates because I haven't stipulated that there is a z direction for it to turn into. So imagine something's rotating, but now I changed the axis to tilt it, right? So now I got to include the z direction. To be blunt, that complicates things kind of a lot. By kind of a lot, I mean a lot. Let's just power through this. I will point out, I will be more careful than ever before about pointing out what's important and what's not, what would be on an exam and what's not, although I think you can kind of figure that out. The stuff that takes me 20 minutes and goes across the board, 3 times will probably not be on any exams because I don't know that I could even fit them into the exam. So hopefully that's kind of obvious. Irregardless, I'll still be quite explicit. Okay, now we're still on 2D, so we're still only rotating in the plane. Now recall that on the first lecture, I solved the wave functions just by some snarky little folding a particle in a box wave function over on itself, figuring out what wavelengths are appropriate. Those, of course, can go into wave functions. Those are like de Broglie wavelengths, and those go into wave functions. I was even able to figure out the energy. Then we figured out the Hamiltonian. The next lecture, we talked about how to transform kinetic energy, double derivative of x, double derivative of y. We talked about how that transforms into, here, just the angle phi. And so we have our Hamiltonian that oddly is almost identical to the free wave, the very first thing we did in quantum. That's why 2D is like a great start, because it's very familiar to you. It should be, all right? If it's not, that's another problem. Except that instead of an x, I have a phi. It's still two-dimensional because phi is, remember, it's arctan of x over y. Remember that from last time. That's just a standard trig. X over y is two-dimensional. So even though that this is a one-dimensional, this is just a double derivative of a variable, it's actually two-dimensional. It is very much like a free wave. It has the same energy of a free wave. Instead of h bar squared k squared over 2m, it's h bar squared m squared over 2I. Now m is a quantum number, 0, 1, 2, 3, 4, 5. It can be negative. Positive is like this, negative is like that. Things can rotate two ways. That's a degeneracy. We talked about degeneracies. I happens to be the moment of inertia. I'm a little worried about the pen, and that is mass times r squared. Now, rigid rotor means that we're assuming that this is a particle on a string, so the radius doesn't change. Of course, here's the radius. Now, when we are talking about a hydrogen atom, we can allow the radius of the circulating electron to change. You'll see how we deal with that. And I don't want to say anything more. It is a little unfortunately complicated. But for today, the radius is fixed. So mass times r squared is just a moment of inertia. So instead of 2 times the mass, you have 2 times the moment of inertia. Now recall that another thing that I really hate it when you people lose points on something really stupid. There are 2 m's. There's m for mass, which I will now write out mass. I will do that on your exam. But now there's an m quantum number. They have nothing to do with each other. People stupidly will lose points on exam when they confuse them. So don't. But if you're not watching this, that's why some people should get C's. So wave functions. Now wave functions are just like a free wave, e to the I m variable. Now again, the variable is no longer x, it's phi. M is our new k. Remember that free waves were e to the I kx, now I have e to the I m phi. So it's very analogous, right? So you're just very familiar, you just have to just change the variable, just change x to phi. And if you can do that, which you should be able to do that, then you're set. Let's see, we also talked a little bit about how the m quantum number, how a boundary condition that it has to bite its own tail, is why m is a whole number. Okay, so last bit, why don't I do this? I didn't talk about normalization, and you folks had a real hard, you definitely are struggling with that, so let's review that. And I'm kind of speaking off the top of my head here. I don't have this in my notes. It should be, I should be able to do this. You should be able to do this too. Definitely I should be able to do this. Okay, I can look at this diagram and I can see that this thing rotates 2 pi. So those are my limits. Wave function, complex conjugate wave function is easily going to be, I'll write it all out, although I hope that it's immediately obvious that I got e to the minus imv, e to the imv. Remember, m, it can, did I say theta? M can be negative, but you don't, that doesn't mean that you put in a minus sign. If m is negative, then it's hiding that within itself. So you just write in m, okay? Now e to the plus something times e to the minus that same something is 1. So I'm just going to, this is e to the 0. Let me just wipe that out, which is 1. And again, it doesn't require high school, it does require high school calculus, not college calculus, to look at this integral and know it's 2 pi. Now on the exam, a lot of you stopped there, and you shouldn't have. The normalized wave function is not 2 pi times e to the im something something. It's 1 over the square root of 2 pi e to the im something something. Well, e to the im phi. Okay. Oh, that doesn't look good. There we go. That looks better. If I don't do it right, the world will explode. Okay. So there we go. There's our normalization, and maybe I'll throw that question at you. I'm not beyond throwing that exact same thing at you on the exam, which I would consider that just a giveaway, by the way. So that means I would have harder questions, because if I did that, because I'm just giving you points. Last bit I wanted to cover, I didn't mention this last time. If, God, I used to bring this up. This is hideous, but recall that we can we can call the Hamiltonian angular momentum squared over 2I, right? Just like when we were in x, y, and z, it's p squared over 2m. P is linear momentum. Here, we're angular momentum squared over 2, not m, but I for moment of inertia. So I can say that this is j squared over 2I. Now remember, that's jz, not the jz, but a jz. And I want to mention that because I don't want you to forget that when I'm talking about rotation like this, which I am, that my head is basically the axle, right? My head is the vector that is the moment of inertia. And right-hand rule, all that stuff, remember that? We talked about that last time. So I can say that this is jz squared over 2I. Now the point of this is that then I could simply take, I can recognize that jz squared is minus h bar squared double derivative of phi. And from that I can figure out that the angular momentum is, and again, this should look stupidly familiar. Just like linear momentum was h bar over I derivative with respect to x, angular momentum in the z direction is h bar over I derivative with respect to the only thing that we have instead of an x is the phi. So again, the momentum thing looks hopefully very, very familiar. What am I going to do with this? It will come up later, so I want you to see this. There's not really a lot to talk about when it comes to momentum, not now. It'll be a little bit more important later. But again, just for review, just so that you are immersed in this, just so that whatever I come up with, it'll be trivial compared to like what we're doing here, what you're doing on occasion on homeworks. Of course, the test will be easier. What I'll do is I'll figure out the average momentum, but I won't do this with the eigenvalue weight. I ought to, that's easy. I'll do the expectation value weight. It's a little bit harder. And I'll do that because I just solved the normalization. Okay. Now the expectation value, it will be the same as the eigenvalue. Now recall that there are problems sometimes. Sometimes our wave functions are okay with energy, but they're not okay with momentum. We ran into that. This is not one of those examples. When we did run into one of those examples, we had to do expectation value. Expectation value always works. In this case, this is an example where the wave function and momentum are okay with each other. So the wave function is definitely okay with the Hamiltonian because that's what it's the wave function of, but it is also okay with momentum. However, I'll just do the expectation value way, really just for the heck of it. All right, so what is that? Okay, so integrate over all limits. Notice on the exam how I tested you on that. That's something that I give you enough information to know it, but whether you use it or not, that's on you. Okay, so wave function complex. Again, that's on a handout. Here's the operator acting on the wave function. Of course, there's only one angle. And this, of course, should speed up time. I'm not going to say what state it is. The ground state would have m of 0. I'm not assuming that. Oh, minus, because it's complex conjugate. H bar over I, derivative, with respect to phi. And hopefully you all are looking at this and realizing that I've already messed up. I didn't put in the normalization constants. Okay, I've got 2 of them, so that's 1 over 2 pi. I actually wasn't testing you, I actually forgot. Anyway, all right, so what do I get now? Again, this should be rather trivial. The derivative brings down Im times h bar over I. That's just, here, I'm going to bring that h bar m. Integral 0 to 2 pi, e to the minus Im phi, e to the Im phi. There we go. Now I recognize this as 2 pi because I just did it, and therefore the expectation value of Jz is h bar m. Okay, recall that for a free wave, the momentum was h bar k. So again, m and k are basically the same thing. One of the other differences is, I've already stated, and we've explored why m is a whole number. We've explored that many, many times, and that's because the wave function has to bite its tail. The free wave in x does not need to bite its tail, because when it gets going, it just keeps going. There's no tail to bite. That's why it's missing a boundary condition. And if we were talking about free wave, and instead of h bar m, we had h bar k, k can have any value, including 0. It doesn't have to be a whole number, because it never has to bite its tail. I'm just, you know, I don't know if I'm going to put that on a test or not. Maybe I should, because that's an easy question. But I just want to point out differences. I just want you to get immersed in this, because this is one of the easier things that we're going to do, because we're about to do 3D. Let's see, the only other thing I want to remind you on is, one of the differences with the free wave is this is the only wave function. You know, it's kind of interesting with the free wave that we had sine, cosine, e to the plus ikx, e to the minus ikx. We still have that plus or minus deal, but we don't have sine or cosine. Remember, I stated that that was because sine and cosine mean that you have an object that's rotating and you don't know which way it's rotating, but that's not allowed. When we do spectroscopy, what I'm going to show you is that a wave function of rotation can be interrogated with light to know which way it's rotating. Now, because of that, you're not allowed to use sine or cosine. You should always be able to tell which way it's rotating, so those are not allowed. So that means that we just stick with either the plus or minus I m phi, and again, the m can be, we put the minus, plus or minus sign, we just lump that in the quantum number. We do that to remind you that it can rotate 2 different ways. Okay, so with that, we need to get to 3D. Oh no, I don't want to scare you, but look, this really, there are 1 or 2 times where it does get kind of difficult. I had you do a homework question, I think it was homework 5. Remember where I said, what's the eigenvalue of r sine theta? I think everyone had that. And then I threw kind of a complicated eigenvalue equation at you. Okay, imagine that, but like it's never going to end and it's harder. That's what we're going to run into 3D. This addition of the z dimension does complicate things. Okay, so there's some of that, but there's also a lot of algebra. Algebra, right, is a middle school skill. You can do it, but it is daunting when you have pages of it. So that I will admit. And one mistake and it's blown, right? Not that we wouldn't give you partial credit. Okay, now real quick, I've got, of course, some coordinates right here. I'll remind you of that. And what I'm going to do is I'm going to write down all of that. We're in spherical coordinates, right? We're doing the 3D. We're going to do what's called the 3D rigid rotor problem. I won't even write that down. Here's your coordinate system. Just the new thing is theta. Theta is like this, and it goes from 0 to pi. And I hope you remember that. You had trig in high school. And I'm going to write down all the trig relationships. I don't expect you to memorize this. I'm just trying to, I just want you to remember it. You should have had trig. You absolutely should have had trig in high school. If not, then here. So you know this. I'm just trying to familiarize you with it, and so that none of this is like mind-blowing. Because it gets kind of on the long side, right? Okay, now, despite the fact that I simply added one more variable, theta, x, which used to be r cosine or sine, I forgot, phi, is now a little bit more complicated. It's r cos, and remember that you just figured these out. You just figure these out with right angles and all that. Again, it does sometimes makes your head spin a little, but at the same time, it made your head spin in high school, right? Okay, so is that right? Yeah. Okay, z is always the easy one. That's r cos theta. Now remember, I also, just to remind you, Remember, mathematicians switch, theta and phi are switched for them. That's awesome. Okay. Note also that I've expressed the Cartesian coordinates in the spherical. Now I have to do the opposite. Now I have to express the spherical in the Cartesian. And hopefully you recall why I have to do that. Let me just write this down. Radius, of course, of all the middle school, high school things that you learned, this is something I don't think anyone could really ever forget. The others can be something I imagine are a little bit daunting. As I've said many times, I particularly have a dislike of the arctangent function. Something just about it just really rubs me the wrong way. So we have the same definition of phi. Of course, we have theta. Theta is our new entrant. And it is not a cosine, it is an arc cosine. So when you're going, one way you use normal trig, the other way you always use those inverse trigs, which no one likes those anyway. So that's z over r. So theta is a little easier. I like arc cosine a little bit better. Okay, now with these, and again, as much as there's a lot here, it's not that bad. You've seen it before. And the trick is, okay, so I'm going to make that go away. The trick is now to apply what we know here to, let's go back and remember where we were very uncomfortable, but now wish we were at now, which is, of course, the Cartesian operator. And of course, I'm going to be writing this out in 3 dimensions. And I'm also going to provide you some enhanced symbologies. These do get so long and complicated that we have to start using symbols for them, because we just do. You'll see. Okay, this is, and I hope you've seen this before. Right, this is called del squared, right, which is Laplacian. So if you need to look it up, Wikipedia, of course, has a table and lots of identities for Laplacians, and that's great. Okay, so now remember, I really wish we could stick with this, but the problem is that we're trying to do hydrogen atom wave functions, and we're going to stop there, but hydrogen is round. So we've got to convert this to our spherical coordinates. Now the way we're going to do that is, and we did a little bit with how to convert Cartesian dx, double derivative of x, double derivative of y, to cylindrical. And I think I have a handout how to do that. It used to be a problem set, I mentioned that last time. To do spherical, that would take, 10 pages of algebra. I'm told that there's if you're a math major, that there are some tricks to get it down to 1 page. Okay, we're not going to do that, and I'm not even going to put a handout. I actually started on it once. I started writing a full description for those of you who just feel like you have to have that. I got I got to the first page and I said, yeah, no, I'm not doing this. Let me remind you how you would begin. And again, this should be familiar to you because it's just the chain rule, I think it's the chain rule. Right, so remember that you just cross out, the change in x still needs to be the change in x. So you can just in your mind cross out the change in r. You have the change in r over the change in r. And you still have the change in x. So it has to be that way. And then you do that with phi. And this is what we did last time. And so again, this at this point should be quite trivial. Just writing this down should be trivial. And what you would do next is, what's the change in r with respect to x? Well, here we have r defined with x. When you would evaluate this, you treat y and z as constants. Change in phi with respect to x is a little, actually, no, it would be the exact same thing as what we had last time. And then we've got a new entrant, the change in data with respect to x, which actually would be 0. So it looks like it might be easier. This one thing might be easier. But then the problem is you have to do the double derivative. Excuse me, you have to do the double derivative, then you have to do that with y, you have to do that with z, and then you have to combine them to simplify them. Okay, now again, that seriously would be about 20 pages of algebra. I'm not even doing that on a handout. So, what is the Laplacian then in spherical? Actually, I'm going to need to take a break and wipe out the board. I told you. I'm going to need to take a break and wipe out the board, and I'm going to write out the 2D to remind you, then you're going to look at the whole 3D. And then we're going to simplify it. So, okay, I better stop talking. So let me just wipe out the board and you'll see that. All right, so I'm going to leave those up there. I hope you can, I can't see the camera, but I hope you can see the identities up there. And now again, recall, don't think that I'm actually working this out. I'm just going to go ahead and cut straight to the answer. But first, let me remind you that in 2 dimensions, maybe I shouldn't do this. I'm kind of working backward. But what I want to do is compare. I want to compare 2D to 3D. It's kind of instructive and it'll help you remember things. Let's see, I've got the double derivative with respect to r. I probably should speed things up. And this is the cylindrical one. This one is not so hard. Now you may be thinking like, wait a minute, just a minute ago I wrote this down and I just wrote down the double derivative with respect to phi, the term I'm writing down right now. What happened to these? Recall that if the particle on a string has a fixed radius, there's nothing to take a derivative of. The wave function, if there is a wave function in the radial, for the radial part, it's just like 1 nanometer. So there's nothing to take the derivative of. So these we assume were 0. And regardless though, if you don't assume that, then they're there, and so I want you to see that. Hint, they're going to come back. When we do the hydrogen atom, the radius is not fixed. So I want you to understand that these are still there. In our model problem, they weren't. And so now let's do 3D. Again, using a process that would confuse the great turkey in the sky that made everything. Let's see, I got my h squared over 2m. Now remember, I'm going to write out mass because we have a new quantum number, which is m. I will always do that from now on. Starts out, it's not too bad at first. We've got the same double derivative with respect to r. And then a slight difference, we got 2 over r. Well, that's a big deal. Single derivative. And then we get the world's greatest nightmare. Now we've got this thing, which really just comes about from z. Okay. There's a way to slightly simplify this. Okay, so here's our new entrant theta. And it's in front of phi. So what bothers me about this is I've got theta and phi in the same expression. Remember that if we're going to do separability, we can't have r's and thetas and phi's in the same expression. That's bad. So I can see that this is not going to be straightforward. Okay, then there's a little pattern to this. Sine theta, dd theta, then sine theta is on top. Now you kind of recognize that problem on problem set 5. It had you. I just made up that little expression, but it kind of looks like this, right? That eigenvalue expression, I think I had you do that for number 1. I called it math practice. It kind of looked like this, didn't it? And that's why, it wasn't exactly this, but I had you do that to kind of get used to dealing with things that look like this. This is kind of the hard one, right? Let me just look at it. Okay, now, told you, right equations across the board. When we do hydrogen atom, we have this plus some more terms, by the way. All right. Now, just like this is the Laplacian, this gets a name because why wouldn't it? I mean, look at it. This is, I want to call it Kim Jong-un, but anyway, it's called the Legendrian. I don't really have these memorized. It's just that every now and then when I'm looking things up on Wikipedia for like notes or whatever reason, I have a zillion reasons. It's good to know this because sometimes I see the words used and it's good to know what it means. Okay, so there you go. Last bit, maybe this will be on an exam. It's instructive to know that things work together. That all of this kind of, it may be across the board. It's not may across the board, it is across the board. But it all makes sense, it all works together. And what I mean by that is 3D should become 2D. There should be a way to modify 3 dimensions by rotating, when we did 3D, this is our new entrant, the theta. If I point theta 90 degrees, then this then 3D is 2D because it's in the XY plane. Okay, if that's the case, notice that if we hold R fixed, these are gone. Now let's look at this thing. If we're fixing theta, to be in the XY plane, theta is 90 degrees, and just like we got rid of R by fixing R, then we would get rid of these terms because theta is fixed, right? So there's no derivative. The derivatives are 0 because you're not taking the derivatives of anything. Okay, then what you have is 1 over sine of 90 squared, sine of 90 degrees, that's, what is that, pi? pi halves? Pi halves, right? So sine of pi halves is 1, so this is 1 over 1 squared. And what you end up with is 1 over r squared dd phi squared, right here. So they end up being exactly the same. Okay, again, I just want to point out that if 2D becomes 3D, we're fixing theta, these terms are gone, this is 1, and then this is basically that. So it all makes sense. Sounds like a good test question. Let's see. All right, last bit. And I am already going to have to wipe out the board again. Okay, what do we do with this? Well, we have to solve the wave functions, right? I've set up the problem. This is the Hamiltonian. It's in spherical coordinates. We'll assume no potential energy. So now I've got a 3D particle on a string. So I'll get rid of the r's. And then I've got to solve the wave functions. Instead of just a wave function for phi, I've got a wave function of theta. So again, our big picture, and I'll write all this down. I know people have told me not to speak equations. I get it. I'm trying not to. It's just I mess up. So what are we going to do? We are going to, I will need to stop here in a second. Sorry, let me look at this. With the Hamiltonian, we're going to solve the wave function. And recall, I told you to memorize this, and absolutely, I'm not pulling your leg. Memorize the fact that when we're solving wave functions, we're checking for separability. We're going to try to separate this into a wave function of phi and a wave function of theta. And of course, they multiply. And they multiply for all the reasons that we talked about over the last several lectures, right? We're going to say R is fixed. Okay, and so that means, of course, that we don't have to worry about these. When we do hydrogen, we do, just heads up. But right now, these are gone. So we're basically just solving this. And like last time, the way we're going to do that is we're going to start with a separable wave function. And let me outline what we're going to do. Is we're going to, so all of this is the Hamiltonian. We're going to apply the wave function, which gives us the energy times the wave function. And then that's on the right. On the left, we're going to divide out that wave function. Okay, so again, I'm telling you the strategy that we're about to employ, and that is to see whether the wave function is separable. The purpose of this exercise is to verify whether the total wave function is separable into these sub-wave functions. If so, it means that this is going to be a lot easier to solve. Not that that means a heck of a lot, but I'll take anything, right? The other thing is that when you write this out, what you're looking for is a phi part and a theta part. Now remember that if a wave function is separable, you apply this technique, act on the right, divide by the left, and then what you need to see is that all of this collapses into two terms that are added or subtracted, whatever. Subtraction is just the addition of something negative. You're looking for two terms, and each term has only one variable. There's no crosstalk. There's no phi sine theta or vice versa. Now, when you've done that, two things. You've proven that the result, that the answer is separable, and each one of these is going to become its own Schrödinger equation, a miniature Schrödinger equation. One of them is actually going to be easy to solve. The other one we're going to look at a math textbook from the 17th century to solve it, but we've been doing that for a while now, and that will be the end of today's lecture. Okay, now I need a few minutes. I'm gonna leave this, wipe out that other board, and we're gonna start on separability. All right, so I'll be right back. Okay, so of course, give yourself quite a bit of room, bit by bit, bit by bit. Now, how do I want to do this? I gotta like plan ahead as I write things down. So 2 times mass. Now you can see that I've got the letter I, so I will be using the letter I for moment of inertia from now on. Okay, now okay, so we are working with this part. So here's our constants, and now I'm going to deal with the Legendre. Okay, so I've got the factor of r squared. Okay, now let's see here. I've got 1 over sine theta squared, double derivative of phi. Now I'm going to write out the total wave function as being composed of the two parts. You don't get anywhere unless you do that. Remember, that's what we're testing. Now the wave function of phi is stopped by this derivative. You can't let it traverse through because you just don't know, you don't even know what this is. If it's a sine or a cosine, that would change the answer. So this can't progress. But the wave function with theta can fly right through because that's a phi. So I'm gonna go ahead and do that. So I'm doing some algebra steps. I'm doing 2 steps at once. So that's what I'm doing. We're gonna be here for like 2 or 3 lectures if I don't take some shortcuts, okay? But look, that's not too bad, right? Okay, so there's that. Now what? Okay, I factored that. So remember, this has been factored. Okay, so now I'm going to do the same thing. Now, as you can imagine, there'll be a wave function of phi there, but I'm not going to put that down. For those of you who are following along well, you might want to go ahead and do that. Let me just write down, again, I'm writing down the Legendrian. Okay, now I'm going to apply the total wave function, and of course I don't know what the wave function of theta looks like, so I have no idea what the action of the derivative results in, so it's stuck. But when I write the wave function of phi, you know, it can actually just go right through. So I'm just going to go ahead and put that there. Okay. In bracket, now you know I'm always tempted to just stop writing, but actually you got to remember that it's equal to something. There we go. Okay, so again, yeah, it's quite a mouthful, isn't it? When we do hydrogen, we're going to do the same thing, except it's even longer. That will be done in 2 more lectures. Okay, next step. I'm going to have to do a couple of steps of algebra at once. Again, if I don't, it'll take forever. Now, what am I going to do? First one's not hard. 2 times mass r squared. Okay, not bad. Let me point this out. Now let's strategize. This is not brainless. I've got to have expressions with phi, and I've got to have expressions with theta. I have a problem, and that is right there. Theta, phi. You know, derivative, wave function, it doesn't matter. U cannot be here. This is clearly theta's guy, because it has a derivative with respect to theta. This is clearly theta's term, sorry, phi's term. That's phi's term. This is theta's term. Sorry about that. Okay, so this is the phi term. So that theta is unwanted, like a red-haired stepchild. So what are we going to do about it? So I'm going to do some algebra. So that's 9. Then I'm going to multiply by sine theta squared. And let's also get rid of that pesky minus h bar squared over 2I. So it's going to end up over here, by the way, right? So I'm going to multiply by the whole thing by this. So, you know what? No, what I said here, that's stupid. That's stupid. Look what I did. That's in my notes. That's in my notes, right? That was dumb. You know what I'm going to multiply by? I'm going to multiply by 2I minus 2I over h bar. You see why? Because then this cancels, then that's 1, right? So, yeah, hopefully you see that. So this is now the number 1. Okay, let's see what this does. So the constants are gone. Okay, so the constants are gone. I've multiplied by sine theta squared. Sine theta squared, this just ends up being... Now, what I'm liking about this is that this, of all the things we've ever dealt with, how bad is this at this point, right? Hopefully you're looking at this and saying, okay, yeah, and guess what? We're looking for a solution. It's going to be e to the im phi. Look familiar? Yeah, it's going to be e to the im phi. I still have to worry about that wave function of theta, but we'll do that next time. Next step. Okay. Sine squared of theta divided by sine theta is, let's get rid of that, okay. Sine theta. Now the rest of it we can't really process, so that just stays put. Okay, equal to minus 2I over h bar squared energy sine theta squared and wave functions. Almost turned into Jar Jar Binks there for a second. Okay, we're almost done. And how am I doing? Sorry, I gotta check Siri again. Hopefully it won't scream at me. I've got just enough time to do the last step. Okay, and now I'm giving my instruction set over here. Okay, so I'm going to divide on the left by looking at what I've done here, I'm not dividing. I'm multiplying by 1 over that. I got to be more careful how I express things, right? I can either say divide by this or multiply by 1 over that. Hopefully, I didn't just throw you off. I just threw myself off. Okay, so when I do that, let's see what happens. I can actually do some of that here. I try never to write things in place because I know that that can be very hard for your note taking. And of course, you have to do it everywhere. This is all, there's no derivatives here, so I can put these things wherever. In fact, I can put them right under themselves. So you can see how nice and clean this comes out. There's no more wave functions or anything. Okay, so again, I just do some middle school algebra. And let me see what I end up with. I end up with 1 over... I now have an expression with only phis in it. And again, that doesn't look too bad. It'll be equal to a constant because now I've got another expression, which certainly looks more complicated, and it is. And this is the part that we're going to look in an 18th century math textbook to solve. And I have, on Wikipedia, they actually discuss the history. This thing, by the way, that we're solving is like one of the most important things that solves like fluid flow. So they knew about this way, way, way back in the day. So there's a whole Wikipedia page talking about this equation here. Yeah, it sounds like fun, right? Let's see. Okay, so I simplified that. There's nothing I can do about this part. And this is equal, I don't want to do this. You know what? Let me also do one last little bit of algebra, and we're going to stop there. I'm going to bring this stuff over. It's minus, so I like it to look like a plus 2ie over h bar squared sine theta squared. That 2 doesn't look so good. Okay. And this is all equal to 0. Okay, so now I do that because mathematicians, I know that you're not mathematicians, but this is how they like to put things. What I find appealing about it is I find it way easier to see the separability. This plus this has all got to be 0. Okay, last bit. Are we separated? Here's the phi, and here is the theta. Okay. Now these suckers have to play off against each other to cancel. Right? They have to sum to 0. The phi part and the theta part have to add to 0 because literally they have to add to 0. And look what I just did. It's 0. Now, hopefully you can also see more about separability and why each one of these is actually a constant. Because how can all, especially this part right here, if this isn't a constant, then if it's like a sine function, plus sine function, then this has to be minus the same function. But how can it do that when this is a function of phi and this is a function of theta? How could whatever this thing comes out to be some kind of function, again, let's say it's sine phi, then this has to be minus sine phi. But how could it ever be that when it doesn't have a phi in it? It's a theta. So the resolution is that each one of these is a constant. Now remember, we've been seeing this over and over again when it comes to separability. Each one is a constant. Now each one being a constant becomes its own mini Schrodinger equation. We could imagine that each one becomes its own energy or something like that. So, with that, let me give you a last hint. We'll end a little early today. Actually, we're on time, and I promised you I would try to end early, and I know I've largely been violating that. Let me point out, last bit, that the wave function of phi, we're actually going to just assume that it is e to the I mp. Exactly what it was in the two-dimensional case. Now, if you do that, then you'll find that this is actually, I think it's like minus m squared. And that means that all of this is plus m squared, where m is a constant, like, again, it's a quantum number, it's not mass. And if this is a constant, this is what they solved back in 18th century Rome or whatever. And that gives you the theta wave function. So I have the phi wave functions. This turns into a constant. Ask an 18th century mathematician, and then they give you the theta wave functions. And then we go from there. That's all for today. And next time we'll start here. Yeah, this is a rough one. We'll start here. Look at the last Diffie-Q. Go look in our 18th century textbook to solve it. Look at the wave functions. I'll hopefully have some computer graphics that'll make up for some stuff. And that will be it. Ooh, and then we're in the hydrogen atom. and after that, then we're done. So, okay, I'm out of time. I'll see you all, I think, Wednesday.